Louisiana State University, and his mini course will be on the Bloch and Fermi varieties for periodic operators and open problems. Right, so hopefully some open problems. Yeah. Okay. Yeah. So I'll just pass it over to you.
Thank you. Yeah. Yes. So after hearing, I want to make sure that everyone on Zoom can also hear me. Hopefully the microphone's close enough. If there's any problem, just let us know. I want to make sure. So I want to make sure that everyone understands everything I'm saying. I'm not sure that's a bit idealistic, but so after hearing Peter's lecture, I got some ideas about how I can modify my lecture to try to fit into the framework of the summer school, which is centered around spectral theory and homogenization and thresholds type problems. And I'll keep that in mind. So I wrote down during Peter's lecture a few points that I want to try to remember and try to give sort of some answers to in some sense. So my lectures in the next 3 days are going to be specifically about periodic operators, and maybe get into a little bit about ergodic operators or quasi-periodic operators if there's any time, and of course there will not be time. But so this is centered on periodic operators. And why periodic operators? Well, it's because, as Peter will show you in his subsequent lectures, when you do homogenization, you look at a structure that you look at a medium that has a fine scale structure. And in the kind of simplest case, that fine scale structure is like a crystal. So it is periodic, genuinely periodic. And so the theory of periodic operators enters into that analysis in a fundamental way. And so the title of my lectures are the Bloch and Fermi varieties for periodic operators. So you see the periodic operators there. But what's the Bloch and Fermi varieties? What are those things, and why do we call them varieties? Variety comes from algebraic geometry. And it's just a word that people use to make it sound scary. But it's really not. So, well, yeah, actually it is. So it's kind of hard stuff when you get into algebraic geometry. The Bloch and Fermi varieties, what these are really relations between energy and momentum, or frequency and wave number. So Peter showed you in his very first discussion a relation between relation between frequency and wave number. And in quantum mechanics, this becomes energy and momentum, quasi-momentum. And so these are really equivalent notions when you go from classical to quantum mechanics. And the Fermi variety is this thing that says, at a particular energy or at a particular frequency, what are all the different wave numbers or momenta that particular periodic structure can support at that energy? Okay? That's called the Fermi surface. The Bloch surface is similar. It just asks a slightly different question. It just says, what are all the frequency and momentum pairs that are admitted by that particular periodic structure? And you'll see exactly what I mean by that. And then this makes its way into homogenization when you take the period to be very small compared to the wavelength. And that's one of the things that I'm going to try to incorporate into my lectures. I'm going to write on the screen like this, and hopefully this works. So let me first give you an overview of what I would like to do during the next 3 days, starting today. And hopefully, well, if I do my job right, you will understand these words and the concepts by the end of Friday. So I'm going to start with just introducing what we mean by Schrödinger and elliptic operators. Schrödinger operators coming from quantum mechanics, elliptic operators being kind of the classical analog, although Schrödinger operators can be thought of as being elliptic, anyway. Continuous ones, discrete ones, and in between, bridging the gap between continuous and discrete. It's things that people call metric graphs or quantum graphs to make it sound more scary. And then I'll introduce periodic operators. And operators is a fancy way of saying, okay, I have a periodic medium, I have an equation like a Helmholtz equation where the coefficients are periodically varying. And operator is simply, this idea of operator, whenever I use the word operator, what I really mean is something right there. Then you hard job for you. So what do I mean by operator? Let's say, for the Helmholtz equation that you just saw earlier today, you had minus Laplacian, actually this had Laplacian. Let's do minus. And then you had minus k squared applied to u equals some f. And so you can think of minus Laplacian plus k squared as being something that you do to the u to get f. And so this operates on the u. And so we call it an operator.
Minus Laplacian minus k.
Yeah, minus k squared. Yeah. So we call that thing the operator. Or we just call the minus Laplacian the operator, and that acts on the u. And if the f is 0, then we're looking at an eigenvalue, an eigenfunction of this operator. And so that's what we mean by operators, is parsing the idea of equations in a way in which the this object here is kind of an input, and you solve for the output, which is the u. And so I'm going to use this terminology of a forcing and a response to the forcing. So this is something that you impose, is force. And this is what you supposedly observe. It's the response of the medium to that forcing. And that's a nice point of view. And that's the operator associated with it. All right, then I'll talk about the Bloch transform. The Bloch transform is the Fourier transform with respect to, it's a discrete Fourier transform that you apply to periodic things. And so I'll show you what that is when we get there. This is the fundamental tool in going from periodic structures to representing them in terms of plane waves, which you already heard about this morning. But you have to modify these plane waves because we now have a discrete kind of structure in which these plane waves are occurring. And I'll explain that also to you. As you know, the Fourier transform, can everybody hear me in the back? Okay. Do I have to yell louder? Is it decent? Okay. As you know, the Fourier transform or the Bloch transform in the context of periodic media decomposes an operator or a function into things that we think of as being exponentials or plane waves. And that's kind of the role of it's exactly the role of the Fourier transform in the analysis of equations in mathematical physics. And so I want to actually prove something that's called Bloch's theorem that tells you how to take a periodic operator and decompose it onto these plane waves so that you can use plane waves as in superpositions to form any forcing and response. So in terms of plane waves. And I want to show you how that proof actually goes. And there's an abstract version of it that is related to decomposable operators. And I actually want to show you that, and I'll get to that tomorrow, I think. Then we come to this thing called the dispersion function, which explicitly addresses the problem that you heard about this morning of dispersion relations between frequency and wave number, or energy and momentum. And we'll address the idea of, okay, as I already explained, this dispersion function which relates these quantities is encoded in these things called the Fermi or the Bloch varieties, which puts it into an algebraic, the context of algebraic geometry. It's extremely natural context to understand the relation between energy and momentum is algebraic geometry because, well, depending on the particular operator, it could be analytic geometry or algebraic geometry or a combination of the two. And you'll see about this. And so it turns out that there's a lot of, there's so many tools the algebraic geometers know about that can be applied. And that's one of my goals these days, is try to strengthen the connections between spectral theory and algebraic geometry, particularly in the context of periodic operators. Some of the consequences of this theory of taking periodic operators through the Bloch transform and obtain the Bloch and Fermi varieties is that you see something that's called a band structure of propagation and stop bands for periodic materials. This is something called a resolution of the identity. You'll see what that's about. Something called the density of states can be written very nicely in terms of these objects. Density of states means how many states do you have per frequency interval, essentially. And then something called binary states. And I want to explain these right now. We'll wait till we get there. One thing that the problem that I've been most interested in that I will allude, actually I'll spend a little bit of time on it on Friday, is this irreducibility or reducibility of this Fermi variety. This turns out to be very interesting because of a paper of Peter Kuchment and Boris Weinberg in 2006. So there's this algebraic geometric object that's, you can talk about whether it's reducible or not. It can be decomposed into two components. You'll know what I mean later on. But what I want to say is that this idea of reducibility is intimately related to whether you can get these things called embedded eigenvalues. You are going to understand what I mean later on. Hard to hear back there? Is it hard to hear back there? Is it okay? So this is an interesting thing. Just keep it in mind. I won't explain it right now, but you will hear a lot about it later. So maybe you just can Google embedded eigenvalues and see what it's all about. And then maybe I say a few words about quasi-periodic operators. All right. Now, next slide. This happened this morning. Some ideas to follow from Kirill Cherenichenko's lecture this morning. And so one of the questions that came up in this lecture was, there are these solutions that can be conceived as waves. There's a particular type of solution that was mentioned that we think of as being a wave, and that is these exponentials of linear functions. Okay, so you just take a linear function of space, which just means you kind of chop it up into parallel hyperplanes perpendicular to the wave number, and then the wave vector, and then you just have a sine or cosine propagating where the peaks and the troughs follow those hyperplanes. Right, so that's a plane wave, and that propagates in time because of this shift. It's time shift. So the time is just shifting the function in x in the direction of k. So this is just a traveling plane wave in the direction of k. These are things that we will generalize when we come to periodic operators, because this kind of solution only happens when you have coefficients that are constant, right? Constant in x and constant in time. But now we're going to talk about operators where, so materials where the material properties vary in a periodic way. It's like a crystal. You see exactly the same structure of a particular period happening over and over and over. So there's a certain amount of homogeneity there. It's kind of a discrete homogeneity. If you shift by that lattice amount, to the right, left, up, down, by a certain multiple of that crystal period, then you get exactly the same structure back. So in that sense, it's kind of like a discrete homogeneity. We don't really call that homogeneous. But you can imagine now that when the period gets very, very, very small, it starts to become homogeneous. And one of the themes that you're going to see in homogenization is how, if that period gets very small, but the wavelength stays like this, that you can start to conceive of that periodic structure as having homogeneous behavior from the point of view of someone who is at a much larger, is looking at it from a much larger spatial scale as the actual period. In fact, that's what all homogeneous media are anyway. They're inhomogeneous at the molecular level. And if you look at the epsilon in view, the coefficients in, say, the Maxwell equations, those are already homogenized. Of course, not rigorously, but I mean, phenomenologically homogenized, right? So, okay. So another one, what's the energy of a plane wave? In quantum mechanics, there is a spooky way of identifying energy with frequency. So the plane wave can be identified with an energy. That's not the same as the energy of a wave packet. So it's a different thing. You would have to integrate over the appropriate thing to find the energy of a wave packet. But there's a way to identify an energy with a plane wave. Okay, so just pay attention that this is going to come up. It's kind of a partial, it's not an answer to the question, but it's an addressing of the question in the context of quantum mechanics. But certainly, we do understand the frequency of a plane wave. And in quantum mechanics, frequency is related to energy in some spooky way, and that's what we'll mean by the energy. All right, inhomogeneous media always possess dispersion. This is a quote from this morning. And you're going to see now that when you have periodic operators, periodic media, you have strong dispersion. And that dispersion is explicitly encoded in this thing called the dispersion relation, the relation between energy and momentum. And it's exactly that object that becomes the algebraic or analytic Fermi variety or Bloch variety. So it's just encoding that information in the context in which you can apply algebraic geometric concepts to it. Although I won't really go in that direction.
So why strong dispersion?
Yeah.
It's going to be even stronger than
It's going to be even stronger because, and I hope to actually allude to that, because the strong dispersion is coming from the fact that you have something that's really called two-scale homogenization, where you have extreme parameters in the medium. I'll try to actually maybe explain, if I can, keep my mind organized enough to do that along the way. What's meant by extra strong dispersion. Okay. Now, length scales. Let's see, what was this about? Oh yeah, so this has to do with the extra strong dispersion. Let's just maybe keep in mind that I hope to try to address this issue that Peter brought up. Yeah. So Keto would understand this. Extreme coefficients, you actually can rescale around the origin, you get bands and gaps. Okay, so for you all back there, I hope maybe some of this will become clear later, but this came to my mind. Also, this idea of eigenvalues for a bounded region. So keep this in mind when we come to looking at the ideas of bands and gaps. Because what we'll be doing is looking at a period of a structure and looking at eigenvalues and eigenfunctions for that period with certain boundary conditions that are not the ones that Tito mentioned for a bounded obstacle, but they're those that are somehow implied by looking for a plane wave with a particular momentum and apply certain boundary conditions just because of the phase shift across the period. And then that gives you a self-adjoint operator that has certain eigenvalues. So that's going to come up in the discussions. All right, so now comes an overview before I even start the actual lecture. So I wanted to give you an overview just so you know, because my point of view today is going to be, I think it's going to be along the lines of sort of classical, what we call harmonic analysis, and kind of the algebraic setting, because I feel that when I understood that better myself, I started to be able to understand certain questions I was interested in with regard to the Fermi.
Sí, va a acabar la 1. No, son varias.
Son varias. Yo
Sí.
pensaba que una sola.
No, empieza uno, le dan un tiempo, ya pasa otro.
To me?
Están en la mar. Este está en Luisiana. Este investigador está en
Was that a question? No, it was. Okay. All right. All right. Okay, so here's an overview. Schrodinger and elliptic operators in, let's say, 3 dimensions, where it makes some sense to us. This here is called a Schrodinger equation, where you take the Laplacian, which you already know is the sum of all the second derivatives with respect to x, y, and z, and then plus a potential, v of x. And then you ask the question, what are the eigenvalues and eigenfunctions of this operator? So what u satisfy Laplacian plus v applied to u gives you a multiple of that u. All right, so in this discussion, in quantum mechanics, it turns out that this minus Laplacian plus v is called a Schrodinger operator, non-magnetic Schrodinger operator. This comes from an electric potential. That's just where it comes from. And then you apply this to a state u, and what you ask is, when is that equal to a multiple E of u? That eigenvalue is called the energy. And let's just accept that from now. It just comes out of a certain procedure that was, of course, developed over, historically. So one can't really go into that. Now, from the point of view of classical, let's say, elliptic operators that you heard about this morning, you have a kind of Laplacian where I put the coefficient inside here, and then you have a sigma, some other coefficient here. And the analog of the frequency is actually this frequency squared here. That's what you saw this morning. So this is a slightly different version from this one here, where the frequency is actually multiplying this coefficient, or the eigenvalue is multiplying a coefficient.
So if my rho depends on x, it will be your sigma.
Yeah.
And if my mu depends on x, it will be your power.
Yeah, your rho, I guess, yeah, your rho would be here. And if yeah, that's right. That's correct. So your rho this morning was out here. Now it depends on x. You actually have to put it inside. Oh, your mu. Okay, you actually have to put it inside. Yeah. I always think of rho as density, but okay, mu is density, and it goes inside. Okay. Oh, no, you're right. I'm sorry. Density goes here. This is where the second derivative in time is. I'm sorry. Correct. Yeah, you're right. I agree. So now, what does periodic mean? It just means that the coefficient sigma, tau, or let's say v, depend periodically on the spatial variable. In other words, there are 3, if we're in R3, 3 independent vectors in R3, v1, v2, v3, which when you scale, when you shift by any one of those vectors, the potential remains the same. So in 2D, this would be one of those period vectors, this would be the other period vector. And I've drawn the picture so that any point, say this blue point right here, if I shift it by v1 or by v1 and v2, or any integer multiple of v1 and v2, then you get to a corresponding point where you will have exactly the same value of v. And so the values of v are determined what they are in this parallelogram, or in R3 a parallelepiped. Inside of that, what we call a fundamental domain, you have certain values of the v, and then you just repeat them according to those period vectors v1, v2, and v3. That's what we mean by periodic. And so the operator becomes periodic. The Bloch of field, we have to think that these fields that generalize the idea of a plane wave. And these are called, they're named after Bloch and Bloch. We call them quasi-periodic. And they have the property that when you add, when you start at a particular x and you shift by one of these period vectors, okay, so if you shift by a period in let's say the jth direction, then what happens, and I call this the shift operator. The shift operator just means I take a function and I shift it by adding vj. That's the sj shift operator. All right, that's an important operator in this theory, and it's nice to think about it as an operator in its own right. Okay, think of shifting as an operation called sj. And so we're looking, these kinds of fields are such that if I shift by vj, the result on the field is that it gets multiplied by e to the ikj. That's very similar to the plane waves you saw this morning. If you shift, you get multiplied by a phase shift, by a phase, because it's exponential. So this is really discrete exponential. If I shift by vj, I get multiplied by e to the ikj. That kj is called a quasi-momentum in quantum mechanics. or you can call it a discrete wave number in the jth direction, because that's how the phase changes as you go in the vj direction. And this e to the ikj, I'm going to call it zj. And this zj is also called a flow k multiplier, because it says that when I shift in a certain direction, the field gets multiplied by this z number. Therefore, the zj here is an eigenvalue of the shift operator. Okay, if I shift, it multiplies by zj. So zj's are eigenvalues of the shift. And if I have 3 different directions, then I have 3 different eigenvalues, one for each direction. Okay, and those are your 3 different flow k multipliers. And the exponent, the k's here and the exponent, those are called the quasi-momenta. And we're going to allow the z to be complex. It can be any number, all right? So this k here is called the quasi-momentum, or the Bloch wave vector, if you think about it in terms of classical ideas of wave numbers. Quantum mechanics, it's the quasi-momentum. And as I said, this zj is our eigenvalues of the shift by vj. And the E is the eigenvalue of the Schrödinger operator. So I've given you two kinds of operators here. A Schrödinger operator, we talked about how the eigenvalues of a Schrödinger operator are important. They're called the energy, and they're physically important because they are related to energies that are observable. Okay, so this is physically relevant. This E here, eigenvalues of the Schrödinger operator. Now we have eigenvalues of the shift operator. Eigenvalues of the Schrödinger operator are physically identified with energy. Eigenvalues of the shift operator are physically identified with momentum. Okay, so this is what momentum and energy are in quantum mechanics. They're energy. I keep saying this over and over. I know I'm repeating myself, but energy is eigenvalue of the Schrödinger operator. Quasi-momentum are the eigenvalues of the shifts. Okay. Now, what does it mean for H to be periodic with respect to these same shifts, the Sj shifts? It just means that the H commutes with the shift operator. And I can just show you this with my hands. If I take a function, I shift it over here and I apply the operator, well, the coefficients look the same over here. Okay, and then I shift back, I get the same thing as if I just apply the operator right away and then shifted it over here. Okay, so first I can shift and apply the operator, or I can first apply the operator and then shift. Because the operator looks the same, the coefficients look the same when I shift. That's the picture, okay? And this is the mathematical representation of that. It just says that the H operator, it's called H because they call this the Hamiltonian. Like this energy operator, or the Schrödinger operator, also called the energy operator. It's also called the Hamiltonian. So that's why it's called H. So the Schrödinger operator commutes with the shift operator, or energy operator commutes with this momentum operator. See? And as soon as you have this, you might know from linear algebra that when you have 2 matrices that are diagonalizable, 2 matrices that commute with each other, you can always find a common basis in which they're both diagonalized. Common basis. That's the power of commuting, or the restriction of commuting, you might say. And so in some way, we're going to expect this H and the shift operators to be simultaneously diagonalizable. There has to be some way. Now we're in an infinite dimensional space, and there's a whole continuum of energies, a whole continuum of momenta. So there's a way to think of diagonalizability in infinite dimensional spaces, okay? And the way we know it as mathematicians is something called a resolution of the identity that allows you to resolve both operators as multiplication operators. So diagonalization is the same as converting an operator into a multiplication operator. So it's local, it becomes local at every point. Okay? And so the idea is H is decomposed on simultaneous eigenstates of H and Sj. So the point of view now is going to be that we look at the shift operator in its own right, keeping in mind that the Schrodinger operator commutes with it. Okay, so we start with the shift operator and look at all of its eigenstates and try to find how we can write down a general L2 function in terms of the eigenstates of the shift. That's Fourier analysis. That's just another way of saying Fourier analysis. Okay, you write down arbitrary functions as superpositions of plane waves. Okay, we'll do that first, and then we'll say the Schrodinger operator commutes with those, and therefore we try to decompose the Schrodinger operator on those sets of plane waves and those eigenspaces of plane waves coming from the shift. That's the decomposition theorem that I'll show you, and that leads to the Bloch theorem. Okay, that's the strategy. Now, as we do that, there comes this thing called the dispersion function, which tells you when I have a certain eigenvalue of the shift. So I look at a certain eigenspace of the shift, right? We're trying to do simultaneous eigenstates. So I look at eigenspaces of the shift. These are quasi-periodic functions. And I say, how does H act on those? There's certain energies, there's certain eigenvalues of H on each one of those subspaces of the shift, eigenspaces of the shift, okay? Each eigenspace of the shift corresponds to a particular Z. Remember, Z is e to the ik. But this Z has, yeah, so this would be, the Z would be Z1, Z2, Z3. This is still the introduction, haven't even started. So this D here, there's going to be a function whose zero set tells you which energies arise in each one of these quasi-periodic eigenstates of the shift operator. And so that's just saying which energies correspond to which momenta. Okay, that's called a dispersion function. And its zero set, you see here, is called the Bloch variety. So you look at all momenta and energies where the momenta, this C star just means all the complex numbers except for zero. You don't allow zero. Okay, so e to the ik doesn't allow zero. Okay, and so you take zero out, and this D is the dimension of the space, RD, not necessarily R3. And so you have one Z for every direction, one quasi-momentum for every direction. That's the Z. It's a vector it's a vector of Bloch multipliers. And the E is the energy. So you look at all momenta and energies such that this D is equal to zero. And that, when D is zero, that just means there exists a U that is a simultaneous eigenstate of both the energy of the Laplacian for energy E, no, the Schrodinger operator for energy E, and the shift operator for momentum Zj. You see? So this simultaneous diagonalizability, simultaneous eigenvalues, and what are the corresponding momenta and energy for those simultaneous eigenfunctions? This D captures that. It says whenever this D is zero, then that corresponding ZE is a pair of energy and momentum that's emitted by that operator. Are people happy? You happy? And then the Fermi variety at a particular energy just says, what are the momenta? It just takes a cross section. It says, for a certain energy, what are all the momenta that correspond to that energy? Now let's do an example of something called graphene. So it's a hexagonal graph here, and the state U will be defined just on the vertices, okay? And I have an operator called A. This is the H, but now it's a discrete one. And I'm going to apply the A to a function. And this is what it does. I'm going to make this very simple. You see, this structure here has two period vectors, E1 and E2. That's the V1 and V2. The V now means a vertex, and this is vertex 2. Sorry about the difference in the notation. But I can shift this vertex by E2 up to here, and I can shift it by E1 over to here, and I get the same picture. So I shift this little black fundamental domain by two period vectors. The operator, this is the operator for what they call graphene. It's the simplest, what they call tight binding model for graphene. Okay. So you apply A to a function. This U here is defined on the vertices to start with. And then you apply A to the function. What's the value at V, say V1? It's U, it's the value at V2, the value at V2 minus E1, which is here, and the value at V2 minus E2, which is here. You simply take these three values and add them up. For people who are missing the minus 3U at V1, I just took it out because it's a scalar multiple. So you just take, you look at this point here, you take the three neighboring points and you add them up. That's what the operator does. It's that simple. And then same thing for the V2. And then this repeats periodically, of course. Send it periodically. Now what I want to do is take that operator and assume that I have a solution that is also pseudo-periodic. So it's also an eigenfunction of the shift, which means that if I shift the U at any V by E1, it gets multiplied by Z1. Okay, that's all it means. A shift gets multiplied by Z1. Shift in the E2 direction gets multiplied by Z2. So I'm saying let U be a function that is an eigenfunction of both of the shifts with eigenvalue Z1, Z2, and it's also an eigenfunction of this operator I just defined right here, which is a periodic operator. They actually commute. So I expect to get a relation between E and Z1, Z2. All I have to do is apply this operator, assuming that this U of V2 minus E1 is actually Z1 inverse times the U. You see? So if I shift in the other direction, I multiply by Z1 inverse, because I'm applying the operator, the inverse of the operator. And so it turns out that I just plug it in and I get, and I ask the question, what's AU applied to V1 and what's AU applied to V2? And now I know that if I have that answer, then I can just repeat the answer periodically because it's assumed to be pseudo-periodic, quasi-periodic. So I just need to apply the operator to two values, V1 and V2. So it's a simplification. And I get this matrix here. Now notice that, so what this is saying is that the V1, the value of V1 only depends on the V2. The value of A at V1 only depends on V2. And that's because over here I showed you the value at V2 only depends on the neighbors. And this is so graphene is a bipartite graph, which is actually relevant here. You get zeros on the diagonal because you don't have self-interactions. That's kind of an interesting thing that arises in this thing, in this matrix. And so you take the determinant, because I want to know when are there solutions of the system where this times V1 equals 0. So I take the determinant of this. That is my dispersion function. D of Z1, Z2, E equals, so I put the minus E here, take the determinant of this, I get E squared minus that thing. Now you can think of, we could talk about this for a couple hours right here. What's interesting is that you get E squared minus something. So if I set this equal to 0, then I get E squared equals something. And just notice real quick, if Z1 is E to the I K1 and K1 is real, so if Z1 is on the unit circle and Z2 is on the unit circle, means we have a real quasi-momentum, then this is just the modulus squared of this quantity. You see that? Because this is just the conjugate of that. And so you get E squared equals, so I set this equal to 0, I get E squared equals this positive function of the modulus. And when that hits 0, this can hit 0 at certain points. These things are called Dirac cones. This is why it happens for graphene, at least algebraically. Anyway, Dirac cones are, this is a picture of K1, K2 versus E. It's called the dispersion relation, the real dispersion relation. And you see these pictures a lot in spectral theory of periodic operators. And you can see that, yeah, by the way, why is it called the dispersion function? The one that you saw this morning was just K, like E equals mod K times some constant. And so that just looked like a cone, right? Like this, both directions. That's because it was homogeneous. There was no dispersion and lossless. Homogeneous, right? Completely homogeneous, no periodic structure. With the periodic structure, you see some interesting things happening. If I were to draw this, and I'll show you this in more detail later. The dispersion has to do with the fact that this is curved. And why dispersion? Why is it called a dispersion relation? Well, evidently it's supposed to tell you something about dispersion of waves. As you saw in Kirill's talk, there was a constant speed independent of the frequency. There was a single speed in the homogeneous medium. That means no matter what wave you start with, what frequencies, they will all propagate at exactly the same speed. But when you have dispersion, this dispersion relation, the relation between frequency and wave number, that's not linear. So you do not have a constant ratio of omega to k. So you do not have a constant speed. And actually what's important is the derivative of this relation, which gives you what we call a group velocity, which I won't go into here because that goes into the time dynamics, but it tells you how a packet of waves at say neighboring frequencies close to a particular one here propagates. And it's the second derivative of that you care about, because that tells you how fast that wave packet breaks up. Okay. And a wave packet breaking up really means that all the different waves that make it up travel at different speeds. So it breaks up. That's dispersion. Okay, that's what dispersion is. And so dispersion relation has no dispersion if it's linear, right? But it's still telling you there's no dispersion. So it's the second derivative of that's important. And that's in quantum mechanics, that's actually related to an effective mass inverse of that. Anyway, those are just some things to think about, that there's a lot going on here in the structure of this object. So what you see here is the real part of the Bloch variety. It's the relation between E and K, all right, which is the title of all my lectures anyway. Now we're starting the lectures. Number one. Now, I knew I was going to take quite a bit of time on this stuff leading up to now. And I still have a certain amount of time to start the actual agenda. And I'm pretty sure I gave myself enough time to finish, but who knows? All right, I'm backing up now to the beginning. So if you missed some things I said before, I'm going to try to catch up on those again, right back from the beginning. What's a Schrödinger operator? Look at examples of continuous ones, discrete ones, and what I mean by in between. All right. In RD, think of these being three, that's the really physical situation. This Hamiltonian, which I described before, has this kind of a form. Now you see a slight variation from the one I gave you before. Without this A, I have minus grad squared, which is grad dot grad, which is the same as the Laplacian with a minus. Okay, so Laplacian is just grad squared. It's the sum of the second derivatives. But now I am taking the grad operator and I'm shifting it by this weird thing, that's square root of -1, times some vector A. Let's see what these things are. In quantum mechanics, V is the electric potential. And so the electric field there is actually minus the gradient of V. There's some electric field going on that's sitting there, supposedly not moving in time, unless it is. That's the V. Then there's also a magnetic potential associated with the magnetic flux field. This B here is the curl of the A. And typically, you would start with an E and a B that you're interested in physically, usually, and then in the operator you find a B and an A, and you see that there's a certain amount of leeway in finding those potentials that correspond to those fields. And these are called gauge transfer. You're picking a particular gauge. So when you hear people talking about choosing a gauge or doing a gauge transformation, on the elementary level, it really started with just meaning what are all the potentials that correspond to the same physical field, right? And there is some meaning to the different potentials. Anyway, there's a quantum mechanical state space, which is L2 of RD. This is a Hilbert space. Quantum mechanics lives in Hilbert spaces. Otherwise, it breaks down as far as I'm concerned, or as far as I know. So it's L2 of RD, square integrable functions on RD. And now the role of this H operator. Now it's interesting that this is a classical. This can be thought of actually a classical electric field and classical magnetic potential. You take those and you stick them into this equation, and you get something called quantum mechanics by some magic, which I do not have time to explain anything about, fortunately, maybe. Anyway, H is what we call the generator of the time dynamics, okay? And you saw this morning that Kito started with time dynamics, and he reduced to a spatial problem when he looked at time harmonic fields, e to the I omega t. I'm going the other way around. I'm saying that this H now is the generator of time dynamics. In other words, in quantum mechanics, this is the time dynamic problem. You take a state and you say the way it evolves in time is through this H. Now you have this I times something called Planck's constant. Planck's constant is something that relates frequency to energy. And this has, there's a lot of history behind this, and there's no way that one can explain. I guess some people understand it, okay, at least at different levels. Certainly better than I do. But mathematically, this is what happens. Okay, think of H as being small, although it's only small from the point of view of humans, because it's not dimensionless. So what do you mean by small? Anyway, it's small. So look, the harmonic solutions, in other words, we look at solutions that look like an initial state times e to the I omega t. These are obviously very special solutions to an ODE. I mean, ODE in the sense that the ODE in a Hilbert space. You know what I mean? So the states in a Hilbert space when you're evolving in the single variable time. Well, if I'm looking for harmonic solutions, that just means those that are oscillating at a fixed frequency for all time, then they look like this by definition. Now, if I plug this into here, this is what you do in ODE class, right? In finite dimensional systems, you look for very simple solutions which are oscillating in time at a fixed frequency. If I put them into here, the idea in harmonic analysis is that, look what happens. Now, pay attention to this, because this is important. This is, I think, fundamental to Fourier analysis. Why does Fourier analysis work? If I plug this into here, I take a derivative with respect to time. And because I have an exponential, what comes out is minus I omega. When I take derivative with respect to time of this, and then I multiply by that, and then take the h bar out, and I get just the e. Okay, so the point is that because what I didn't say is that the Laplace, the Schrödinger operator also commutes with time shifts because it's independent of time. So as far as time is concerned, I can use any frequencies I want. I don't need like quasi frequencies. Any frequencies I want. So what's the point? E to the I omega t is an eigenfunction of the shift operator, which is the same thing as saying it's an eigenfunction of the t derivative. Shift in time, right? Same as, because what? Shifts are generated by derivative in time, okay? Infinitesimally. So commuting with time derivative is the same as commuting with the time shift. And so, since I commute with time shift, I want to look for solutions that are eigenfunctions in time, in the time shift, which are just exponentials. That's why Fourier analysis works. That's why we use it, because you decompose functions you decompose into eigenfunctions of the time shift, which are just exponentials, right? That's what we're doing. So that means that this is an eigenfunction of that. So therefore, I plug it into here. This just becomes E times C. And I set that equal to HC. Therefore, looking for harmonic solutions is the same as looking for eigenfunctions of the Schrödinger operator. And I plug them into here, the eigenfunctions, and the eigenvalue goes up here with the Planck's constant. Okay. And this is a spectral problem for the Schrödinger operator. That's why there's a whole huge, humongous community of mathematicians studying the spectral properties of Schrödinger operators. And some people are so busy with that, they don't even go back to the time dynamics. But they intend to. But they never do. Sometimes they never do, right? And I'm guilty of that. But I intend to come back to the time dynamics, really. Okay. Now let's look at a discrete Schrödinger operator on ZD. I already showed you one on a hexagonal lattice. Now let's just look at the regular old ZD lattice. ZD is just the integer lattice in D dimensions. This is called a tight binding approximation. So the V here is still a multiplication. So the variable is n equals n1, n2, n3, etc. up to nd. That's a vector of integers. And when you apply the V, that's just a multiplication operator in the n variable. Okay? Already multiplication operator, already diagonalized. But the Schrödinger operator, what's that? Well, you just add up the neighbors. So I take, at this point, I add up the value here, 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 and here. All of the neighbors that are connected by edges to that point, I just add up those values. And then I can subtract 2d times un because this is related to taking a discrete second derivative. But since this is a constant, people just usually scale it out and put it into the E, put it into the energy. So they don't have to deal with it in the analysis. So it's common just to get rid of this, although physically it should be there. Okay. Now there's, this is the discrete Schrödinger operator called the tight binding approximation. It's very difficult to rigorously derive, but that's what people use. Now there's something called a Harper model that extends this to magnetic Schrödinger operators. I just want to show you what it is, but I won't dwell on it. So associated with every edge, you have something called a magnetic flux, and I'll call it Bn and An for the nth vertical and horizontal edge. You take these values and you think of them kind of as phase shifts, in the sense that the new Schrödinger operator, a magnetic one, looks the same as before. See, these are just the sum of the neighbors, but with these extra phases, as if there were a kind of quasi-momentum behind there. And it turns out the momentum and magnetic potential have the same units, and they're actually they're really kind of the same thing in quantum mechanics. Maybe I'll show you a little more about that later. So you can do magnetic, discrete magnetic operators. And in the special case of a constant magnetic field B, what you do is you take, let's say, I have to take a particular, let's try to find the simplest potential, which consists of ANs and BNs, that give me a particular field. So we need to look at a discrete curl. What does that mean? It means I take the sum of the A's and the B's as I go around in the appropriate direction. And that tells me what the magnetic flux is through that cube. And if I want the magnetic flux or field to be a constant B in each one of these, well, I can take 0 here, plus 2B here, plus 0, and then minus B when I come back. That gives me a B. And then I go 0, 3B, 0, minus 2B gives me B. And so this is no longer periodic. And that's my point, because you have to put B, 2B, 3B, and so on. So as soon as you have magnetic field, you go out of the periodic regime. unless the B is rational, which is really strange. And for some of you who know about this, there's some pictures going back to Hofstadter that showed something called the Hofstadter butterfly, how the spectrum depends very, very delicately on the magnetic field. And there's some about graphene also, in such a way that when the field is rational, you see bands and gaps. When it's irrational, you have a Cantor spectrum. So that's very interesting stuff, and people work hard on that, even like probably right today. Yeah, probably Jake Philman is working on that as we speak. If you all know Jake. All right. And then there's these things called metric graphs, and I'll wrap up in 5 minutes. Metric graphs in quantum mechanics are called quantum graphs. These turn out to be really interesting in their own right. It's kind of a cross between the continuous model and the discrete one. You have a graph, but the Schrödinger operator actually acts so that the states are not defined in all of space, and they're not defined just at the vertices, but they're literally defined along the edges of the graph. So locally, it's a 1D analysis, but globally, it acts more like a partial differential equation. Well, it depends how things are hooked up. See? And so on each edge, you have this ordinary differential equation. But then these edges are all connected together by vertex conditions. And the domain is, you have to, for those who are interested at this point, the domain consists of H2 of each edge so that you can apply the second derivative. And then you have traces, the derivatives and the values. And for this particular, so one of the common conditions is called a Robin condition, where you take the sum of the derivatives going outward from a particular vertex, and that is a certain multiple of the value, and you tacitly assume continuity. Also called delta vertex conditions, I think introduced by Pavel Exner, at least. I don't know if he introduced it, but going way back to Pavel Exner, called these delta conditions. And there's delta prime conditions. Now, let me give you a little overview of what I would like to start on next time. Here I now come, I seriously am going to start this Bloch transform. And this will be, it might seem technical to you all, but it really is what I would like to say is the right framework for this. It's the classical harmonic analysis framework, where you literally look at the Z and the E and the relation between the Z and the E in a very algebraic way. And you define this thing called the Bloch transform, which is the Fourier transform with respect to the shift. Sometimes also called the Gelfand transform or the Z transform, because it's so natural that it has so many names, because everyone discovers it if you think long enough, because it is there, right? And you might say it's not invented, it's discovered, but I won't get into that. But it's like the integers, it's extremely natural. And we make up everything else. No. So I'm going to talk about the ZD as a translational symmetry group. In other words, you look at all translations by these elementary vectors. That's a translation group. It's a group of translation operators. Okay, it's a group because it's closed under addition and it has multiplication. You can go one way or the other way, so it has inverses and so on. So that's a translational symmetry group. And if you want to do a little homework before tomorrow, you can Google free actions, symmetry groups, fundamental domains. So you'll see this all tomorrow, and I'll try to be really careful about it. Fundamental domains, some examples. And then I look at this induced action on functions where I shift a function. See, first I shift points. Now I put that shift inside of a function, so I'm actually shifting the function. And when I take an L2 function and I shift it, it has the same L2 norm, right? Lebesgue measure, right? That means it's a unitary transformation. So we're actually looking at Z2 for you who know who like this point of view. This is a representation, a unitary representation of Z2 on L2. On the states. And so your unit, it's a unitary group of operators. And there is spectral theory, there's well-established spectral theory going back way long time ago, that tell you how to take a group of unitary operators and do essentially a Fourier transform, a spectral decomposition. In this case, it's explicitly Fourier transform. And then take any operator that commutes with that and write it as a multiplication operator. You decompose it. And that's what we're going to do. And I want to do it somewhat abstractly for you because I have found that, what you want to do, of course, is I want to put away some of the details of the Schrödinger operators. And are they differential operators? What's the domain, et cetera, vertex conditions, throw it away. Let's look at unitary groups of operators. Look at the spectral theory of decomposing a Hilbert space with respect to this group of unitary operators, and then show how any operator that commutes with those can be decomposed with respect to that decomposition coming from the unitary operators. Okay? And then we directly apply this to periodic operators, and out pops all these nice things that I told you about. All right. So I guess in my plan of action, if I go back to my my initial, where to go? My outline. Today I did 1. And then next time I'm starting 2. And so I have 2 more days to do 2, 3, 4, 5, 6, 7. All right. And I'm gonna do it. Okay. All right, see you tomorrow.
Okay, thank you very much.